Welcome to Advanced Linear Algebra. Today we are diving into a fascinating and powerful concept known as the minimal polynomial. Imagine you have a complex programmable robot and you need to find the absolute shortest sequence of commands to completely shut it down. In the world of matrices, the minimal polynomial is exactly that, the most efficient, stripped down mathematical off switch tailored for a specific system. Let us explore how this works. Now that we understand the goal is to shut down our matrix robot, let us look at the rules. Why does this concept matter? Because in mathematics, efficiency is everything. We often plug a square grid of numbers, or a matrix, into an algebraic equation. If the result is a grid filled entirely with zeros, we say the polynomial annihilates the matrix. The minimal polynomial is defined as the polynomial of the smallest possible degree that successfully achieves this annihilation. To ensure there is only one unique answer, we require this polynomial to be monic. This simply means the number multiplying the highest power of the variable is exactly 1. It is the shortest, most basic equation that starts with a plain variable. Before we find the shortest sequence, we need the master code. This formula gives us the characteristic polynomial, which is guaranteed to shut down the matrix. Conceptually, it comes from subtracting a variable from the diagonal of our matrix and calculating its determinant. Let us break down the symbols. P of x represents the characteristic polynomial itself. A is our original square matrix. The variable is x. The symbol I stands for the identity matrix, which acts like the number 1 in matrix math. Finally, det stands for the determinant, a calculation that squishes a matrix down into a single descriptive number. A famous rule called the Cayley-Hamilton theorem guarantees that if we plug matrix A into P of x, the result is exactly 0. If the matrix grows larger, the degree of this polynomial increases. Knowing that the characteristic polynomial always works, this formula leads us to an important realization. The minimal polynomial is actually hiding inside it. Conceptually, because the minimal polynomial is the absolute smallest equation that annihilates the matrix, it must perfectly divide any other equation that also makes the matrix 0. In this relationship, P of x is the larger characteristic polynomial we just found. M of x is the smaller minimal polynomial we are looking for. And Q of x is just whatever is left over after the division, known as the quotient. This division rule tells us a massive secret. The minimal polynomial must contain the exact same base roots or eigenvalues as the characteristic polynomial. If the matrix has more redundant information, the quotient Q of x becomes larger, leaving a smaller, more efficient minimal polynomial M of x. Before we move on, let us see this with a concrete example. We are given a specific matrix A and we are asked to find its minimal polynomial to see how it compares to the characteristic polynomial. This matrix has the numbers 2, 2 and 3 running down its main diagonal and zeros everywhere else. Because it is a diagonal matrix, finding the master equation is very easy. We simply look directly at the diagonal entries, which are our eigenvalues. The eigenvalue 2 appears twice, so its corresponding factor is squared in the equation. The eigenvalue 3 appears only once, so its factor has a power of 1. This gives us our characteristic polynomial, P of x, which has a total degree of 3. Now that we have our master equation, let us try to shrink it. We want to test smaller, stripped-down versions of this polynomial. We guess this shorter equation as our minimal polynomial by taking each distinct root exactly once, completely dropping the squared power on the x minus 2 term. But we must test if this guess is correct. To do that, we plug the matrix A into this shorter equation to see if it actually results in 0. Whenever we subtract a plain number from a matrix, we must attach the identity matrix I to the number. This ensures the matrix subtraction works properly and legally, aligning the numbers down the diagonal. Continuing with our test, we perform the subtraction inside each set of parentheses step by step. The first matrix is the result of A minus 2i, where we subtracted 2 from every diagonal entry. The second matrix is the result of A minus 3i, where we subtracted 3 from every diagonal entry. We are now ready to multiply these two resulting matrices together. When we do, the final result is indeed the zero matrix. This proves that our shorter guess worked perfectly to shut the system down. The minimal polynomial has a degree of 2, which is strictly smaller than the characteristic polynomial's degree of 3. Physically, this means our matrix had redundant information that we successfully stripped away. Having just calculated this, let us visualize exactly what happened. On the screen, you see a flow diagram representing our polynomial roots. On the left is the characteristic polynomial we started with, containing the roots 2, 2, and 3. The arrow in the middle represents the process of finding the minimal polynomial, acting as a filter that removes redundancy. On the right, you see the resulting minimal polynomial, which retains only the unique roots 2 and 3. This diagram teaches us that while the minimal polynomial shares all the same fundamental roots as the larger characteristic polynomial, it strips away any unnecessary repetitions whenever possible, leaving only the essential mathematical key. Now that we have seen a successful reduction, we must ask, does this always work? The answer is no, and understanding why is crucial. Sometimes the minimal polynomial cannot be shrunk. In advanced mathematics, certain matrices have tightly linked and dependent internal structures, known as Jordan blocks. Even a tiny addition, like a single non-zero number just off the main diagonal, completely changes how the matrix behaves, compared to a purely diagonal matrix. It prevents the matrix from being easily broken apart or simplified. When this happens, we cannot strip away any information without losing the ability to turn the matrix into zero. Let us look at how this plays out mathematically. Let us test this idea with a new example. We are given a slightly different matrix B, and we want to find its minimal polynomial to see if that extra number prevents shrinking. This matrix has 2's on the diagonal, but it also has a 1 sitting in the top right corner. This is our Jordan block. We start by finding the characteristic polynomial first. Just like before, the eigenvalue 2 is repeated twice on the main diagonal. Therefore, the factor containing the x minus 2 is squared in the master equation. The total degree of this characteristic polynomial is 2. Following our previous method, we will test the absolute shortest possible candidate for the minimal polynomial. We do this by dropping the square entirely, leaving us with a temporary guess of x minus 2. We will plug the matrix B into this short equation to see if it has enough power to annihilate the matrix. We substitute the matrix B in place of the variable x, remembering to multiply the number 2 by the identity matrix I so the dimensions match. This sets up a simple matrix subtraction problem. Let us perform the subtraction to see the result. When we subtract 2 from the diagonal, we get zeros there. But the result is clearly not the zero matrix. That pesky 1 in the top right corner survived the subtraction process completely untouched. This means our test polynomial failed to shut the machine down. The degree of 1 was simply not strong enough to annihilate the specific matrix structure. Because the shorter version failed, we are forced to go back to the squared version. For this specific matrix, the minimal polynomial is exactly the same as the characteristic polynomial. Physically, this tells us the system's internal dependencies cannot be decoupled. So we have proven that not all matrices can be simplified. This brings us to a crucial question. Why does this matter in the real world? The minimal polynomial is the ultimate diagnostic tool for a matrix. It tells us immediately if a matrix is diagonalizable, which means it can be simplified into a clean diagonal grid of numbers. A matrix can only be simplified this way if its minimal polynomial has no repeated roots, meaning no squared or cubed factors. In fields like quantum mechanics or control systems engineering, simplifying a matrix makes calculating the future state of a system infinitely easier. If the minimal polynomial reveals that the matrix cannot be simplified, engineers know they must use more complex tools. We have covered the full topic, so let us reinforce the most important ideas. First, the minimal polynomial is the smallest, simplest algebraic equation that can turn a specific matrix into zero. Second, it is intimately connected to the characteristic polynomial, perfectly dividing it while sharing all the same fundamental roots. Third, it acts as a mathematical filter, stripping away unnecessary repetitions whenever the matrix structure allows it. Finally, it is a powerful diagnostic key that unlocks the knowledge of whether a complex system can be neatly simplified or if it must be handled in its complicated form. You now have a solid understanding of minimal polynomials. Great work!